Okay, so the next thing we want to talk about in lecture 14 are mixtures and solutions. And of course, these occur in many different forms, so they can be from things we typically think of when we think of mixtures and solutions like salt water, right, where we're mixing water and common table salt. They could be things like solids like steel, which is actually a mixture of iron and carbon, and of course often other things, or gases, things like air, where you're mixing nitrogen and oxygen and other gases together. Now we're going to specify at first just to binary solutions, but we want to have a general way of thinking about all these different kinds of solutions. So, um, and so we want to use our thermodynamic language, and so we're going to introduce some notation first, which I think you should have seen before, but let's just review it. So the first thing is we're going to often talk, when we talk about these binary solutions, in terms of mole fraction. So the definition of mole fraction in a binary solution will be that the mole fraction of A, which we'll write as XA, is just the ratio of the number of moles of A to the number of moles in the system. So we can write that as Na over N total. And then if we have a binary solution, we'll often refer to the second component as XB, and that will just be, where the second component is B, and then the mole fraction of B would just be the number of moles of B over the total. And so we know just by definition here that then XA plus XB must equal 1. Okay. Similarly, we can define a concept of partial molar volume, because we know that if we think about the volume, that the total volume, right, must be related to the volume of A and the volume of B, and we can write that as the partial molar volume of A times the number of moles of A plus the partial molar volume of B times the number of moles of B. So where V bar is of A is the partial molar volume of A. Okay. And now the thing we have to note when we write down an equation like this is that in general, VA and VB are functions. This is a function of NA and NB. That is, it's not to say that the partial molar volume of A is just a property of A. It depends on what you're mixing A with. So depending on how much A and how much B you have, A may have a different partial molar volume. So we can look at this expression and note that, okay, this must mean, right, just from differential calculus, if we were looking at a change of the volume, just by formal differentiation here, that should be equal to the molar volume of A times the change in the number of moles of A plus the partial molar volume of B times the change of the number of moles of B. And then we can get contributions from not just changes in the number of moles, but changes in the molar volume itself. That is, so we have terms that are Na dVA bar plus Nb dVB bar. Okay. But there's a problem we observe when we get to an expression of this form, and that is that we note that we don't actually get to change four things independently. So we don't actually have the ability to independently vary Na, Nb, Va, and Vb. That is, we know that in general, the volume is a function of how many moles of each substance we have at some constant temperature and pressure, right? So once we choose the number of moles, the volume is set. We don't get to independently choose the volume fraction of each of the species. And we know that typically, because that's the case, because we know volume depends on NA and NB, we typically can write dV as dV dNA at constant NB T and P dNA plus partial V with respect to NB at constant NA T and P dNB, right? And these expressions look very similar, but obviously it looks like something's missing, right? Here we only have a dNA and a dNB. Here we had 4 things that we could vary. So the only way that these two can be satisfied is if this term here is 0. And that's known as the Gibbs-Duhem relation. And the Gibbs-Duhem relation says that when we have a situation like this, what it implies is that this must be 0. And so the Gibbs-Duhem relationship in this case says that NA dVA plus NB dVB must be 0 in order for these two both to be satisfied. And so there's a relationship between any change. So this implies there must be a relationship between any change in VA and any change in VB, right? And in particular, that relationship must be that dVA is equal to minus NB over NA dVB, right? So if we make a change in VB, there must be a corresponding change in VA, and vice versa. Now, we can make a similar analysis, Gibbs-Duhem analysis, of the free energy, the Gibbs free energy, because we know for the Gibbs free energy, dG is equal to dG dNA at constant temperature, pressure, and NB times dNA plus dG dNB at constant TP and NA dNB. Okay. And we now recall by definition of our chemical potential that, well, first of all, NGM is equal to G, that is the number of moles times the molar free energy is equal to the free energy, and that we define the chemical potential to be the derivative of G with respect to N. So we can define a chemical potential for each species, and the way we'll define that is that mu A is the partial of G with respect to NA at constant temperature, pressure, and NB, and mu B is equal to the partial of G with respect to NB at constant temperature, pressure, and NA, right? So the chemical potential of A tells us how the free energy of the system changes as we change NA. The chemical potential MB tells us how the free energy of the system changes as we change the number of moles of NB, holding everything else constant, right? And so when we write this expression, what we're actually writing is dG is equal to mu A dNA plus mu B dNB, right? But we also know that G must equal mu A NA plus mu B NB because the total molar free energy, or the total free energy, must be the free energy per mole of A times how much A we have plus the free energy per mole of B times how much B we have, right? So the molar free energy is equal to mu A XA plus mu B XB, where all I'm doing here is dividing by the total number of moles and using my definition of XA and XB. Okay, and so since we have this expression and this expression, doing a similar Gibbs-Duhem relation as we have up here, what this implies is that d mu b must be equal to minus NA over NB d mu A. So this tells us that if one chemical potential increases, the other decreases. Just as we saw here, if one partial molar volume increases, the other has to decrease. And the relationship between them is set by this Gibbs-Duhem relation, right? That relates the two. Okay, so that's some sort of general notation and concepts we'll use, and now we'll talk a little bit more specifically about the free energy of these binary solutions.